Hello, everyone. Thanks, Nazli, for the warm introduction and also inviting me to give a talk. I'm so glad to see a lot of familiar faces and at least be virtually back to Georgetown. I wish it was like physical talk, but yeah, COVID times. So yeah, so glad to be here and thanks for inviting me. Let me share my screen. 1 second. So can you see on my screen?
Yes.
Yep.
Okay. Loading. Cool. So today I'm going to talk about some of our work at AI2 on adapting transformer models for document level natural language tasks. And I was fortunate to have great collaborators on this line of work. You can see their faces and names here. So I'm going to give you a quick background on current state of the art in NLP. And for those of you who work in this area and already know about this, sorry if I'm boring you, but I just want to make sure that everyone is able to follow the talk. So recently, transformers are the main models that are being used in different NLP tasks and applications. And these are basically a type of neural networks that consists of two main parts, self-attention and a feed-forward network. And people have used these networks, stacked them together on multiple layers, and then using self-supervised pre-training on large amount of data, people have got very good results using these models. It turns out that you don't need to have large amount of labeled data. You can just use like train this on language modeling tasks. For example, predict a masked token given its surrounding context. And then when you train it on large amount of data, the model parameters are trained so that it transfers very well to downstream applications. And perhaps the most well-known of these networks is the BART model, which is currently, everyone knows that and everyone is using it. And if you look at the results on NLP benchmarks, like the GLUE benchmark, this is a benchmark consisting of several NLP tasks. Most of them are sentence level semantic tasks. And you can see that we are already past human performance. And most of the models, I think all of them are pre-trained transformers. And this figure is like created 2 or 3 months ago. I'm sure there are many more models that are even outperforming these results today. So does this mean that NLP is practically solved? I want to argue that not necessarily, at least for document level tasks. I want to argue that existing transformers are not optimal because they mostly focus on representation learning of words and sentences. And they might also not work well in low resource generation setting. For example, if you want to use a pre-trained sequence-to-sequence transformer model, still, in order to adapt it to your target domain, you need a decent amount of training data. And lastly, I want to argue that these are not efficient and won't scale to long documents. And this is mainly because of the self-attention component of these networks, which is bottleneck. So in this talk, I'm going to talk about three works that we did and try to address some of these problems. So first one, we call this SPECTER, which is on document level representation learning using citation-informed transformers. So our goal is basically representing documents as like an embedded feature or like a vector that you could use in your neural network for your downstream application. This is very useful in various applications like paper recommendation, search, classification, and other document level tasks. So our main goal is doing document level representation learning. And ideally, we want to have task-independent representation. Like if you have a document, how can we represent it in a unified way so irrespective of the downstream task, it performs well. And our goal is also to be able to easily plug this into any application. As I argued before, existing language models mostly take advantage of token-level contextual information. And the most widely used ones are autoregressive language modeling or masked language modeling. In autoregressive, you predict the next word given the previous words, and masked language modeling, you mask one token and try to predict it using its surrounding context. But these do not use any corpus level information. For example, if you have some reason to believe that, for example, two documents are related to each other, these models do not use this information at all. So in SPECTER, we want to use both of these information, both the corpus level context and also the pre-trained transformers that use token level context. And we basically use inter-document relationships to learn better document representations. So in scientific documents, we have this citation network, which provides a good indication of relatedness between papers. If we know that two papers are citing each other, there is a much higher chance that they are related to each other than two papers that do not cite each other. And because we have access to a very large citation network, our hypothesis in this work is that if we can pre-train these transformers on also the citation network, maybe we can learn better document level representations. So SPECTER stands for Scientific Paper Embeddings Using Citation-Informed Transformers. But how can we do this? How can we use both citations and the paper text to produce improved representations? So if you're familiar with BART, the first thing you might try as a baseline model, like if you have a paper and you want to embed it as a feature, is just pass the title and abstract of the paper to the BART model or the pre-trained transformer and get a vector corresponding to the first token. For those of you who are not familiar, it looks like this. You will have some special token called CLS at the first position of the sequence, and then you pass it through BART and take the representation corresponding to this first token as the embedding of the whole document. This basically works well if you have like a sentence level task. But again, our goal is to be able to pre-train this on the citation signal. So what we do, we basically pair each query paper with a related paper and an unrelated paper. So this way, we get 3 representations for each triplet of papers. And the goal is basically to tune these representations so that the embedding of the query paper is close to the related paper while it is far away from the unrelated paper. And to do this, we basically use this triplet loss function that tries to pull together the related and the query paper and push away the unrelated and the query paper with some sort of margin. So, but how do we choose the related and unrelated papers? For positive ones, we basically use the citations. So if two papers are citing each other, the cited paper is the related paper that we use. And importantly, we consider 2 types of negatives. One of them is like random, easy negatives. Like if 2 papers are randomly drawn, they're probably not related and can be used as the negative ones. We also consider another type of negatives, which we call hard negatives. And these are papers that are related to the source paper, but maybe not as related as a direct citation. There are a lot of ways that you can formulate this. What we decided to do was taking the citation of a citation. The hypothesis there is that, okay, the citation of a citation that is not cited by the main paper is still relevant to the main paper, but maybe not as relevant as the direct citation. So this could help the model to learn about edge cases or learn about harder cases. So to train this, we trained this on semantic scholar citation network. We sampled some triplets, and it was about 680,000. And for the transformer model, we used SciBART, which was trained on scientific text. In order to evaluate this, we wanted a benchmark of document level tasks in scientific domain because this model was mainly trained on scientific data. And we wanted to evaluate this model so that the representations are good for a wide variety of tasks, not just a single classification task. So these are the tasks that this benchmark includes: document classification, similarity detection, citation prediction, and recommendation. I'm not going to go through the details of how we constructed these tasks, but if you have questions, please ask me later. And we considered a lot of baselines, which at the time were the state of the art in this task. And you can see the results across a wide variety of these tasks. I don't expect you to read all the numbers here. The takeaway is that, like, if you average performance over all of these tasks, you can see that SPECTER improves over all these models by a good amount of margin. For example, for comparing with the SGC, which is a graph neural network-based baseline, we get about 3% improvement, which is significant. Also, we wanted to see how does this compare with the SciBART model, because what SPECTER does is basically tunes a parameter of SciBART so that it is better able to predict related papers. And you can see that on the right side, we have embeddings of SciBART paper. I'm sorry if this font is very small, but these each color is showing a different category of papers, for example, business, chemistry, society, and so on. And you can see that using SPECTER, we get clusters of documents that are topically more close to each other than using the SciBART, which suggests that the model is actually learning topical information using these relatedness signals. Okay, this works well. We had some offline recommendation tasks among our evaluation suite, but we wanted to know how well it works in the practice. So what we did an online experiment. We first used like Elasticsearch ranking and compared this with a model that has embeddings compared with a model that does not use these SPECTER embeddings. And we saw that using the embeddings, we get 46% click-through rate over the Elasticsearch rankings. And with a model that does not use embeddings, we get 20% improvement, which shows that actually users are finding these papers more relevant than before. So what is helping this model? So we use title and abstract of the papers only because for many papers, the full text may not be available. And also transformer models are limited by like 512 tokens. I will talk about that later in the talk. We see that if you remove abstract, we lose some performance. And we also try to use other information like venue or authors. And surprisingly, we didn't see a lot of improvement. And also, we actually saw performance decline. This was surprising to us because, yeah, you intuitively expect that if you know who are the authors of this paper, it should help you get better embeddings. But we have some hypotheses for this. Maybe the word like tokenization that we use, which is for BERT, is not great for authors because like most of them are out of vocabulary and it breaks authors into smaller chunks, and these are not representing that author very well. And also we see that if we don't use any hard negatives, we lose about 1.5% improvement. And if we do not use a scientific BERT and use BERT large, for example, we get 2% lower score, which shows that why using a scientifically trained BERT and also using hard negatives is important for this task. So one important thing about the SPECTER is that it allows you to use it as fixed representation. So if you get an embedding, you can store it, index it, and then use it later. You don't need to do any further fine-tuning. If you're familiar with BERT-based models, even if you have a pre-trained model, you need to still fine-tune it on a task. So we wanted to see how this works compared with fine-tuning models. And interestingly, we see that SPECTER with fixed embeddings is able to outperform SciBERT when fine-tuned on downstream tasks, even if you take it in a multitask way and train it over all of these tasks. So, okay, good. The results are good, but now we want to, I want to talk about a few of the applications that the SPECTER is powering. One of them is recommendations. Right now, if you go to Semantic Scholar, you can like create feeds. You like add a few papers to your feed, and then based on the SPECTER embeddings, it is able to recommend you similar papers that are relevant to it. People have also used it for search and recommendation. Like there are a couple of websites on COVID dataset that use SPECTER embeddings. And also some people, one of them is here, have used the SPECTER successfully in their research application, and looks like it's working well. So to recap, our goal in SPECTER was to provide a general embedding model for scientific papers, and it achieves strong results across a variety of tasks. For future, we want to investigate inclusion of other metadata. Like I showed how authors and topics are not helpful here, and we want to investigate more carefully why is that, and are there any other ways to incorporate this information. And also, the hard negatives that I described was one of the ways that you could form the triplets. Maybe there are other ways that result in better performance. And also, we didn't use any full text information. And if you can use this, it definitely will improve the quality of SPECTER. So SciDocs and SPECTER are both available. So if you're interested in this type of work, please check them out. Okay, should I go ahead or this can be interactive?
I think that because we are recording and to put this later on YouTube channel, it's better that you finish your talk and then we go to talk.
Okay, sounds great. All right, I continue. So, and the second part, I'm going to talk about generation. This work is about extreme summarization of scientific documents, which we call TLDR. So we all know that the rate of publications is growing every day, and it's very difficult to keep up with the latest development. And this makes summarization very important. But you might argue that, okay, why we care about summarization of scientific papers? Papers already have abstracts. But I want to argue that abstracts are also long, especially if you're processing a long list of papers. For example, you're searching for a keyword or a concept, and then you get a list of results, and you want to decide whether you want to read it or not. Or you get like an archive list of papers every day, and you want to process it. Right now, it looks like this. If you're subscribed to Archive, it sends you emails every day like this, and then you have to probably quickly scan the abstract to see whether it's worth reading or not. So we want to say that basically, if we can have like a single sentence summarizing the entire paper, that would help me a lot of time. That would save me a lot of time to be able to process papers faster and decide whether I want to read them or not. So this is what motivated TLDRs, which are extreme summaries that summarize the entire paper in one sentence. They look like this. They incorporate information from different sections of the paper. It's not like you can extract one sentence from paper and then it represents the whole paper. Actually, you need to do a lot of abstraction and get information from different parts of the paper to form a single summary of that paper. So in this work, we introduced the SciTLDR dataset, which is a dataset of extreme summaries. It includes about 5,400 TLDR instances, and it is multi-target, meaning that for each paper, we have multiple TLDRs. This is important because as the compression rate goes higher, there's a higher chance that you get multiple valid summaries for each document. And this is expert annotated. So this is a table in the paper that compares SciTLDR with other existing data sets. And what is important here is the compression ratio, the ratio of the full length document compared to summary, which is magnitude higher than the existing data sets. And also, it is one of the few data sets that has multiple summaries for each document. So how do we get this data? If you're familiar with OpenReview, this is an open reviewing platform that some of the conferences are using it. For example, iClear is using it. And it allows people to review papers in an open way, and everyone can see this. It asks people to also provide a TLDR of their paper. For example, for this paper, the authors provided this TLDR. So one easy way to get data is just like scraping OpenReview for these TLDRs. We also wanted a second set, which basically captures the reader's point of view. For example, if the main point that other people might say about your paper might be different than what you deem as the most important point. But at the same time, we can't have a crowdsourcing task to like give papers to people and ask them to write TLDRs, because this requires domain expertise. And even if we have domain experts, it would be very expensive to ask them to read the whole paper. So what we do, we basically try to create TLDRs from paper reviews instead of from scratch. Again, if you go to OpenReview, you can see the reviews that reviewers wrote for your paper. And basically, like I think most of us or all of us have seen reviews or reviewed for conferences. And we usually also try to summarize the main points of the paper in one paragraph of the review. So what we do, we basically try to ask the annotators to take the peer review, get rid of the excessive details or criticism or other things, and just take the first paragraph and try to synthesize it into a TLDR. And we believe that this is a good approach because the peer review summary already summarizes the main points of the paper. So an annotator has an easier time to try to condense it into a TLDR. What's interesting is that when we take these TLDRs and compare these with the author-written TLDRs, we see lower lexical overlap, meaning that they're probably capturing different information. I'm going to talk about that a bit more. And also, it turns out that TLDRs that are written from peer reviews are more abstractive, meaning that you can't extract information. They include more novel words. This is expected because they've already gone through one level of abstraction. So we did some information content analysis between the TLDRs that are written by authors and TLDRs that are derived from peer reviews. We basically categorized TLDRs into these 6 categories. These are the information that each TLDR contains. For example, the area or field of a study, that could be like dependency parsing. It could be about the problem, like catastrophic forgetting. It could be about mode of contribution, like method, proofs, and so on. What I want to highlight is that for some of these, we see that peer reviews tend to talk more about how this paper is contributing or what are the details of the method that they're using. Whereas the author written ones are not necessarily including those information. On the other hand, we see that author written TLDRs are putting a lot of focus on the value or significance of their work. Like, it seems that authors say that, okay, our work is the state of the art, our work is novel, it is easily applicable, but the peer reviews do not include those information and do not care about that. So, okay, these were some information about the SciTLDR dataset. Now that we have a dataset, how can we generate TLDRs? You can take as baseline a pre-trained transformer model that is pre-trained in a sequence-to-sequence fashion, meaning that it is trained. You don't have just one stack of transformers, you have 2 stacks of them, and the first one tries to encode the source, and the second one tries to decode it into a generated sentence or sequence. So we take BART and we also further train it on the XSUM task. XSUM is an extreme summarization dataset in the news domain. And this makes sense because it helps the model to learn about the extreme summarization in general. So there are some problems with BART. We saw that it works relatively well, but needs a large amount of training data. And we can't scale TLDR to the scale of XSUM. Comparing TLDR with XSUM, XSUM has about 200,000 instances, but TLDR is just 5,000. So what do we do? Our solution is basically what we call CATS, which stands for Controlled Abstraction for TLDR with Title Scaffolding, which what it says is basically a simple training regimen for TLDR generation. And its main goal is to address the data scarcity issue. It's based on 2 previous line of work, scaffolding tasks, where you introduce an additional scaffolding task for supporting your main task, and also based on control codes that are used in generation, where you add control codes and it tells the model to generate in a controlled way. It looks like this. Like on the bottom, we have our main training data from SciTLDR. And then we also add the paper title task, like saying that, okay, sometimes instead of generating TLDRs, generate the title of the paper for me. And in order to tell the model which one to generate, we append this special character, TLDR or title, to the source and basically shuffle the training data and ask the BART model to generate this for us. And the good thing about this is that there's a lot of data about paper title pairs. You get this for free. And therefore, we expect this to work well because titles also include some salient information about the paper. And you can see the results here, comparing CATS with extractive and abstractive baselines and also BART. We see that it improves over them for most of the cases. So these are 2 different evaluation settings. The first one is when we only use abstract as the source. And the second set of columns is when we use abstract introduction and conclusion sections. And we basically see that in both cases, we get improvements over the state of the art. So, okay, great. Rouge is good. These were results using Rouge evaluation, but we wanted to actually see how well these work in practice. We did some information nugget analysis and also the accuracy of the TLDRs. We emailed the authors and asked if the TLDRs that we generated are good, are accurate. There were 3 levels: mostly accurate, partially accurate, or inaccurate. We see that cats is basically on the same level as gold TLDRs in terms of informativeness, like in terms of information nuggets that it includes. In terms of accuracy, we didn't see difference between the BART generated TLDRs and also our CATS model. Both of the models have reasonable accuracy of 2.5. Again, in this scale, 3 means mostly accurate, 2 means partially accurate, and 1 is inaccurate. So this means that the TLDRs that we generate are usable. And yeah, in summary, in this work, we introduced this task and the data set, and also this simple training regimen for generating TLDRs. So the application of this, one of them is like this. Right now, if you search a paper on, for example, semantic scholar, you get a description of its work, which is like the abstract, and it is kind of collapsed so that you get more papers in one view. But our goal is to make this like this, that for each paper, we just generate a single sentence that tells me what this paper is about. And then I can decide whether I want to read more about that. So yeah, that was about TLDRs. And finally, I want to talk about Longformer, which is our model on scaling transformer models to longer documents. Again, as I said in this talk several times, transformer models are state-of-the-art and many natural language processing tasks. But most of these tasks that people have evaluated on are short documents. And you know, natural language is not just short documents. There are many long document tasks such as QA, summarization, classification, and search. And for example, in Semantic Scholar, 90% percentile of the paper length is about 7,000 tokens. And if you take state-of-the-art models like BART, their limit is 512 tokens. So you can't pass longer text into BART. But why is that? If you're familiar with transformers, they have this self-attention module that works in quadratic complexity in sequence length. This is because each token attends to all other tokens in the sequence. And if you take this, it's basically a matrix multiplication. And if you increase the sequence length, it exponentially grows. So how does prior work try to address this, scale this to longer documents? There's one line of work that avoids working with long documents overall. So there's this MRQA benchmark that is collection of question answering dataset. They take the existing question answering datasets and remove the questions if the answer is not in the first 800 tokens of the document. And the other line of work is basically chunk, extract, combine. So you take the long document, you chunk it into smaller pieces, you extract the information that you need, and then you combine it back into global representations. But the problem with this is that when you are doing the chunking and process information within each chunk, you don't have access to information from other chunks necessarily. So it loses global representation power. There's some recent work on adaptive transformers to long documents, like compressing memory, optimizing self-attention computations, like sparse transformer, BP transformer, and so on. But there are some limitations with most of them. Many of them only evaluate on character language modeling tasks. It's not clear if they work well on actual NLP tasks. And usually they don't do any pre-training. And we know these days that pre-training helps. So these models are basically mostly evaluated on language modeling. So this is our model, Longformer, which basically tries to avoid the computation of the full attention matrix. So instead of having all tokens attending to each other and do this matrix multiplication, we try to have tokens to only attend to one sliding window. Like intuitively, each sentence, for example, if you want to predict a word in each sentence, you don't want to have access to the first token in the document necessarily. So just a local neighborhood should be enough. With this way, if you stack many layers, we get still a large receptive field. And each token will have indirect access to longer tokens as well. So this allows us to basically break this n-squared attention to a linear attention pattern. We also introduce other types of attention. In order to increase the sliding window, we can also use dilated sliding window. This is similar to WaveNet, what people used in audio and speech processing, where you dilate the local attention window with gaps between them. And also, we finally tried some global attention, where we asked all tokens to attend to special tokens in the sequence. For example, you might know that the first token, which is a special token, is important, and I want all the tokens to have direct access to it. And this global attention is task specific. For example, in QA, BART models work like this. They have a special CLS token. You add the question first, then add a separator, and then add the document itself. So in this way, we ask the model, ask all the tokens to have direct access to question and the first CLS token. This way allows the model to be able to use direct information flow. And for classification, we do the same, but we ask all the tokens to have direct access to the first token, which is CLS. This way, we combine both local and global attention into a single pattern. And the attention matrix looks like this. Okay, this works great in theory, but how do we implement this? It requires some sort of banded multiplication that is not supported in existing deep learning libraries like PyTorch or TensorFlow. So what we can do is basically two tricks. One of them is sliding chunks. We break the attention matrix into chunks, smaller square chunks, and then try to do the multiplication using these squares and masking out irrelevant like cells. The other implementation is writing a custom CUDA kernel. But writing a CUDA kernel is very painful. It requires low-level GPU programming. What we did instead, we implemented this in TVM, which is a high-level language that you compile Python code into CUDA C++. And it's easier to use than writing CUDA from scratch. So these are the like how it works in terms of performance. You can see that like the orange line on top is the loop implementation, where you can just write a simple loop to do this multiplication, but it's very slow. And on the bottom, you can see the memory consumption. And the blue one is basically the full attention matrix. And you can see that it can't scale to longer documents, but both implementations are able to scale well to long documents. These are the results on language modeling. We see that Longformer outperforms all of the previous models on character language modeling on two of the standard benchmarks for these tasks. On larger models, we see that Longformer is competitive and comparable to other language modeling models. But these are some tricks on how we train the character level language modeling. We started from smaller window sizes, and on subsequent phases, we increased the window size. And we started from the sequence length of 2,000 tokens. But what is more important is like I use this in pre-training and fine-tuning fashion. Like our goal was to have a BERT-like model that can process long documents for NLP tasks. So how do we convert BERT or the subsequent version of it, which is called Roberta, into a Longformer? We basically first increase the size of the position embedding. We don't initialize it randomly. We take the 512 tokens of BERT and just copy it around. And then we use continuous masked language model pre-training on a corpus of long documents. And we copy the linear projections as a separate projection for global attention. And these are the masked language modeling perplexities. The lower number is better. You can see that if you take the Roberta itself and then adding these further pre-training, we can decrease the perplexity, meaning that the model is better able to predict the masked token. So we evaluated this on a bunch of downstream tasks, question answering, classification, and for classification, we use global attention on the CLS token. For question answering, we used global attention on all question tokens. And for co-reference resolution, we didn't use any global attention. And these are the results. Comparing the Roberta base and Longformer base, we can see that in all cases, we get notable improvements. And this directly comes from using information across the entire document instead of using a smaller window and just slide it over as Roberta does. And we even get the state-of-the-art results on two of the question answering datasets, WikiHub and Trivia QA. And on one of the multi-hub question answering dataset, we get competitive results. This data set is called Hubba QA, and a lot of models are very complicated in this task. They use graph neural networks and entity encoding, but ours is much simpler. It's just a Longformer-based model. And these are the ablations. We basically see that increasing the sequence length is helpful. We see that if we don't do any mass language model pre-training, we lose about 6.6 points. And if we don't use any global attention, we significantly lose a lot of performance. So Longformer, in conclusion, is an efficient and effective model for processing long documents. And most importantly, it's very easy to use. So if you're familiar with the Transformers library, you can just import it and import the model in 2 lines and as you import BERT. So it should be very easy to use. In future, we want to try this on sequence-to-sequence tasks, such as generation. We already have some work on this, so stay tuned. And we want to do longer and better pre-training, and also try longer sequences. We have some internal experiments on encoding up to 32,000 token documents, which covers a lot of, like most of the documents that we have in NLP so far. And we also want to encode the document structure. Right now, the structure that Longformer achieves is like flat. So the main takeaways from this talk is that first, we always use the inter-document, we always use the token level context for training language models. Maybe we can use corpus level context and inter-document relationships. And we can see that this is helpful for learning document representations in scientific papers. We can see that auxiliary and related tasks like generating titles can be helpful for improved text generation. And finally, we can see that we can sparsify the full attention matrix and basically scale it to long documents. So thanks for your attention. Again, this was a great collaboration with many of my co-authors. Thank you, and please, if you have questions, I'll take them now.